Alright, so we talked about the motion, mechanical vibrations, where you do not have damping in the last video. But from now on, we are going to discuss about a motion when you have damping. But still, we assume we do not have an external force or a driving force. So since we do not have a driving force, our differential equation will be still homogeneous, but we have damping. That means energy drains out from the system, for example, because of like fraction. So we do have this 2 lambda times dx over dt term in the differential equation. Okay, since this is a second order homogeneous differential equation, the approach that you would take to solve this will be auxiliary equation, right? So we can write the auxiliary equation as m square plus 2 lambda m plus w square is equal to 0 here. Okay, now let's use the quadratic formula. So ax square plus bx plus c we can find the roots by, well, the roots are negative b plus or minus b square minus 4ac over 2a, right? So these are the roots will be. So let's find the roots in this auxiliary equation in the general sense. And nice thing happens. So let's see. B is 2 lambda. So here it's actually negative 2 lambda plus or minus. B square is 2 lambda square. That means 4 lambda square. Minus 4 times A is 1. C is W square. Okay. Over 2 times A is 1. So it's 2. M negative 2 lambda plus or minus. We can take out a 4 from here. Now when you take out a 4, it goes through the square root. So when it comes out, it becomes 2. 2 times lambda square minus w square over 2. Now, remember I said we choose our damping, the coefficient in front of the damping term, or what concern with damping, we said it's 2 lambda. Why didn't we tell it it's just lambda? Why did we have 2? The reason is to make our simplifications easier here. Do you see why? Because we can divide each term here by 2, right? Then what we really get is the two roots are negative lambda plus or minus square root lambda square minus w square when you divide by 2. So that is why we had 2 lambda to make our simplifications really easy. Alright. Okay. Now here we have 2 roots, right? One root is negative lambda plus lambda square minus w square. The other root is negative lambda minus lambda square minus square root lambda square minus w square. So this is m1, this is m2. Now, okay, now what is the general solution look like? Well, we have a slight situation, right? Because still we don't know what is lambda, still we don't know what is w. It's unknown. So depending on the numbers you have for lambda and w, you can get different scenarios. Do you remember this? When you have the auxiliary equation, remember we discussed 3 cases: distinct roots, repeated roots, and complex roots. Do you get those 3 scenarios played out in these 2 roots? Well, you might say, look, we have m1 and m2, two distinct roots. But no, really it depends on lambda and w. See what happens. Now assume if lambda square minus w square, whatever you have inside the square root, assume it's positive. Now what's inside that square root, or lambda square minus w square, that is the one who decides the whole scenario. Okay, so if lambda square minus w square is positive, you are taking the square root of a positive number, which is completely a valid normal thing to do. So then really m1 and m2 will be distinct. Do you see it? So then we will get distinct roots. So that's the case one. Now think if lambda square minus w square is 0. So then the square root of 0 is 0. So what are the roots? M1 will be negative lambda, right? So because this part is 0. M2, what is that? That is also negative lambda. So you get repeated roots. So if lambda square minus w square is 0, then you get repeated roots. Then I think you can already see what's happening if lambda square minus w square is negative. So you are taking the square root of a negative number. So then all of a sudden you get complex roots. So depending on the type of roots you have, you write the general solution in a different way. So this is actually not where we stop. This is the application of section 4.3 really. So in the sake of this first video, we only discuss what happens if lambda square minus w square is positive. That means when we have distinct roots. Okay, so we are going to divide this lecture into 3 cases, just like we study section 4.3, because it represents 3 physical explanations too. Okay, we'll get to that. But okay, so let's say we have 2 distinct roots. Okay, now damping coefficients and the spring coefficients, or the lambda and w square. So lambda and w square are positive numbers. So really what you get is m1 and m2 are negative roots. So the roots will be negative. Well, if you have distinct roots, what is the general solution? Well, x is c1 e to the m1t plus c2 e to the m2t, right? That is how you write the general solution. The complementary function, right? Solution for a homogeneous differential equation is a complementary function. Now, you assume that you have distinct roots. Now what happens? Now can you tell me the physical explanation of this solution? Let's analyze this. Tell me what is the limit when t goes to infinity, limit of displacement. So limit of this what you have here. Remember, m1 and m2 are negative numbers. So when time approaches to infinity, what happens to this term? This is a e to the negative something. Okay, negative exponent. So this is an exponential decay. So it will approach to 0. This term will approach to 0. So the solution will approach to 0. X will approach to 0. Here's the physical explanation. Now x0 means what is the physical explanation of x0? Again, what is x? X is the displacement. Displacement 0 means what is the position of the mass? We have to go to the discussion, the beginning discussion, right? So in the very first lecture we discuss, okay, we have the spring, let's forget about it. We attach a mass, so it's going to attach it's going to stretch instantaneously from S, and L plus S is the rest position, right? But then when the motion happens, we measure the x, the displacement, from the rest position. So if x is equal to 0, that means the mass, the motion reach to what? Rest position again, right? x0 means you do not have a motion, you do not have a stretch other than the rest position. So really the physical application, the application of these 2 distinct roots when there's a damping, is then actually the displacement will be 0 eventually. And it does make sense. Think, what is the whole purpose of damping? Damping means energy gets small, energy drains out, right? Not small, energy drains out. So when you have friction or something like that in the system, you can see the motion of the mass, but the speed or the motion will gradually become small, and it will totally stop. The system will stop, right? So what happens is the system will approach to the equilibrium position or the rest position. Okay, so that is the physical meaning when you have distinct roots. Okay, or when you have lambda square minus w square is positive. Now you can see these are exponentially decaying functions. Okay, so really this motion or the displacement decay exponentially fast. So what can you deduct about the damping from this situation? Damping is pretty large, right? Or damping is pretty strong, right? Because you quickly approach the equilibrium solution, or the rest position, or the displacement will stop exponentially fast. You can see the behavior of the solution. It's exponentially decay behavior. So we can say damping is pretty strong. Because of that, we say this is an over-damped system. Okay, so you get a over-damped system when lambda square minus w square is positive, or you have distinct roots. Okay, distinct real roots, not complex, distinct real roots for the homogeneous differential equation for the damped case. Okay, all right. And then the motion will be, do you expect an oscillatory motion? No, right? You will not really get a oscillatory motion in this scenario. Oscillatory motions means you have sine and cosine. But in the solution, really, do we have sine and cosine? We don't, right? All we have is exponential functions. Exponential decay functions are like this, right? That is the shape of an exponential decay function, where else the oscillatory motion is like sine, cosine curves, right? Since we do not have sine, cosine, behavior in the solution, so your motion will be non-oscillatory. Okay, so the displacement, the x will behave like exponentially decay dominated. Okay, so the motion will be a non-oscillatory smooth motion where it has a behavior of an exponential decay. Okay, all right, so we'll see an actual problem in the next video. Thank you.